Right, so good afternoon, everybody, and welcome. My name is Krisztián Póra, and I'm currently a developer at SZTAKI. And today I would like to talk about our research and some of our developments with distributed deep learning with Horovod. Uh, so during this presentation, I will start by laying out some of the theoretical basics, why we do distributed deep learning and how we do it, and also introduce one of the more prominent frameworks, Horovod, which was developed for distributed deep learning. Then I will shift the focus to our research and our work by first introducing the environment in which we work, which is the ELKH cloud and some of the services that we provide there. And then I will keep the focus on Horovod, our Horovod solution, Horovod reference architecture, and show some of the developments that we have done regarding this solution and also the research that we have done in order to further develop it. And I will finish off with a short demonstration of how exactly this system works in practice. It's about why exactly we do distributed deep learning. As you know, with deep learning, we are basically dealing with neural networks. We want to train them, and we want to train neural networks that have a large number of layers. This large number of layers basically means that the number of trainable parameters is exponentially increased in these networks, which makes them better suited for solving complex tasks. However, it also makes the training of these networks very, very resource intensive. This means that we need a large volume of training data in order to train them, and also the required time is significantly increased because it can take days or even weeks to train such a neural network. And these resource requirements for a long time limited the application of deep learning. But we have a number of different solutions that make this easier. One of these is the GPU accelerators. These are the graphical processing units or GPU cards. And when compared to our traditional processing units, the CPUs, they can only perform simpler operations. However, they can perform many of these operations and in parallel, which makes them great for deep learning, as in deep learning, we typically use very simple operations, typically matrix multiplication and such. And we can use these GPU cards to uh, train the neural networks with great performance. We can also connect multiple of these cards together. For example, we can have 8 GPU cards within a single machine. When we increase the resources found within a single computing node, we talk about vertical scaling. Of course, this has its limitations. We cannot just keep adding and adding more and more GPU cards to the same compute node. There are some physical limitations here and other limitations such as the actual memory of these GPU cards. The communication between the CPU and GPU cards also has to be considered since it is still the CPU that starts up the actual processes of the learning. And so another solution that helped us a lot with accelerating the training is actually using multiple of these computation machines in parallel, which we refer to as horizontal scaling. In this case, we basically connect multiple compute nodes. These are typically homogeneous. And we connect them using a network connection, which makes this network a very important factor in the success of our training, as our machines will have to continuously and periodically communicate with each other throughout the training. So it is very important that the network is of the right speed, because in distributed training, the network bandwidth is very often bottleneck, since the communication steps need to happen pretty frequently, and if the network is too slow, the entire process will be slowed down. We have two main methodologies for distributing the training process. These are referred to as data parallel and model parallel training. The difference is nicely visualized on the graph on the right side here. In the data parallel solution, we basically take the same model to each of our compute nodes, and we train the same model, however, with different partitions of our training dataset. This can be applied in cases when the model is small enough so that it fits into the memory of a single GPU, for example. In the model parallel case, we do not partition the dataset. Instead, we partition the model itself. Of course, this is to be used when the model is too large to fit into a single GPU. A very important factor when talking about distributed learning is the scaling efficiency, which is basically a parameter that tells us how efficiently we have scaled out our operation. We want this, of course, to be very efficient, because if the scaling is inefficient, then it is not worth it to buy additional compute nodes. But we'll see about the practical examples of scaling efficiency later. Now, I want to talk a little bit about how Uber started experimenting with distributed deep learning. They have a pretty large engineering department, and they very actively use machine learning. And they wanted to start training large models. They increased their utilization of machine learning, and they wanted to train these models on large volumes of data. Of course, they quickly ran into the problem that training with such a large volume of data means that the training time is very, very long. And of course, as a business, Uber would want to lower this training time as much as they can. So they turned to distributed deep learning and started looking around in the field. First, they turned to distributed TensorFlow. They already used TensorFlow for their deep learning operations, as it is one of their most common and widely used frameworks. Now, they met a number of challenges when using distributed TensorFlow, and one of which was the modifications that they had to perform on their training code, the sequential training code, in order to execute it in a parallel fashion, were often complex and unclear. So it was not really clear how to parallelize a sequential training script. And also the actual results, the scaling results that they have got were very, very far from optimal. You can see some of their results on the right side on the graph. Here we can see the training on two different models, the Inception and the ResNet models, and we can see the results scaling up from one GPU to 128 GPUs. And what we can see actually is that at 128 GPUs, we are close to half of the desired performance, which would mean that half of the GPU card's capacity would go to waste. Of course, this is a huge problem for anybody, since these GPU cards are very, very expensive, and you would want to utilize your infrastructure as optimally as possible. Now, this ideal scaling that we can see on this graph basically would mean that when we apply multiple nodes or multiple GPUs, our desired result would be that a single GPU rate gets multiplied by the number of GPUs, meaning that if I use 2 GPUs, that would mean double the performance. Now, of course, this is just a theoretical value. We can not really achieve a 100% scaling efficiency, because the network communication will always mean some overhead, but you can try to get as good a result as possible. And that was what motivated Uber in order to research more into the field, basically to find a solution to better utilize its GPU capacities. And so Uber actually came up with their own framework, a Python package named Horovod, which is an open source tool for distributed deep learning. And it actually supports multiple frameworks such as TensorFlow, Keras, and PyTorch, meaning that the different teams that utilize different deep learning frameworks could parallelize their code and execute the trainings distributed manner with Horovod. Now, it is fairly easy to use because just a few lines of additional code are needed to our sequential training scripts, and then we can perform the training on possibly hundreds of GPUs. It is very important that Horovod utilizes the data parallel execution, meaning that we partition up the data and train the same model on each of the compute nodes. We can see the graph nicely demonstrating the process on the right side, where we can see the different steps of this training process. All the training processes mean a separate GPU. And all these training processes access a different part of the training dataset. They train the model, meaning they calculate the gradients or compute the gradients. And then at step 3, where the averaging of the gradient happens, there is a communication step where the workers, our Horovod workers, average the gradients among each other in order to keep the model consistent. Then basically we have the average gradients and the whole process starts anew, and this is executed multiple times during the training process. Now, Horovod is fairly successful. As you can see on the left side graph, it can achieve much better performance when compared to distributed TensorFlow. Even on 128 GPUs, it has achieved close to 90% scaling efficiency, meaning that we can much better utilize our resources. Now, a disclaimer here that these results were published in 2018, and since then the scales of the power scales have tripped a little bit, and distributed TensorFlow has received a significant upgrade, so now it's a much better solution also. But back then when Uber published these results, this was the scale between the two. Now the actual training strategy that Horovod uses is called ring or reduce. Now going into too much detail, as the name suggests, this is happens in a ring-like fashion in which the workers continuously communicate with each other in so-called rings. Basically, at the communication step, a worker will send data to one other worker and get data from one other worker. This means that everybody participates in the communication, which also implies that the speed of the overall process will depend on the slowest worker because we have to wait for each of them. So if we have 3 fast workers and just 1 slow, that would mean that the entire process will get slowed down because we'll also always have to wait for the slow worker. Now, it is important that this solution is bandwidth optimal, which is very beneficial for us since we have talked about it before that the network bandwidth is very often a bottleneck in distributed deep learning. And so this round-like communication happens periodically during the Horovod training process, depending on a number of parameters. Now, to turn the attention a little bit to our research, I would like to introduce our environment in which we conducted the ELKH cloud, which is an OpenStack-based cloud from Hungary. It supports the Hungarian scientific community with fairly significant compute resources. And it also provides cloud services for more than 150 research projects, which include both national and international. There's also significant support for AI-related research on both hardware and software level, and some of this I will talk about a little bit later. We also participate in the European infrastructure landscape and participate in projects such as EGI-ACE or the SLICES project. And thanks to EGI, ELKH Cloud also participated in the AI for Public Policy project as a pay-for-use provider. Now, of course, one of the goals as an infrastructure provider for ELKH Cloud is to provide the right hardware resources for the research community. However, the difficulties that the researchers face do not end there, because even after getting access to the right kind of hardware, they still have to establish some digital research infrastructure, set up different services and softwares, and they aim to effectively utilize the resources that they have been given. Of course, this is also beneficial for the provider themselves. So with ELKH Cloud, we try to support researchers beyond just providing them access to hardware, and we try to support them on a software level as well, and we do so with the ELKH Cloud reference architectures. These are basically quickly and easily deployable digital research infrastructures with which we try to cover a wide variety of use cases and some of the most prominent tools that researchers utilize. So we have different solutions for distributed deep learning, workload management, container orchestration, and many general solutions as well for different development environments such as JupyterLab or Visual Studio Code. These tools are all open source and up to date with the fresh software versions. They are based on the infrastructure as code principles. They are built using very widespread tools such as the infrastructure provisionment with Terraform, the configuration manager Ansible, and Docker for the containers. We intend to provide the long-term support for these solutions, and we'll see how we realize this exactly. So if you're interested in some of these reference architectures, you can find many of them on the website of ELKH Cloud, which is sciencecloud.hu. And you can see that we have a variety of options, many of which deploy for you a cluster into the cloud, or some of them just deploy a single machine with the right software packages. A little bit about the background of how these reference architectures works. I mentioned that some of our main tools are Terraform and Ansible. We use Terraform in order to provision the infrastructure. Basically, this means the creation of virtual machines, network settings, and firewall rules. And we also use Terraform in order to invoke the second part of the process with Ansible. So this means basically that the user with a single command can deploy their infrastructure. Ansible is responsible for the configuration of our nodes, meaning that it can install packages, start up services, or Docker containers. From the point of view of the user, they can basically visit our catalog of reference architectures, find the right one, and then download it. After downloading, they have to complete a couple of different steps. They have to set their authentication information. So this is used to access their project within the cloud. They have to set some resource parameters, such as the parameters of the virtual machines to be created. Of course, there are virtual machines available of different sizes and configurations, so the user has to specify what kind of resources they can use. There's also a customization option, which can be seen in the bottom right picture, where the user can, for example, customize the passwords for accessing the different deployed interfaces, and also enable some additional features of the infrastructure. And then lastly, with a few commands, they can deploy this digital infrastructure into the cloud and start utilizing it. The reference architectures all have their own user manual and documentation, so they can follow a step-by-step guide. I also mentioned that we intend to support these reference architectures on the long term, and one of the ways we achieve this is through automated testing. So in order to keep up the reliability of these solutions, we set up an automated testing system using a CI/CD pipeline in order to automatically test these systems each week. And if any problem occurs, we get a notification about it, so we can keep these solutions error-free. Turning back a little bit to distributed deep learning, I would like to share more details about our solution for Horovod, the Horovod reference architecture. For this, you can see a nice architecture graph at the bottom. Of course, the goal with this is to support a distributed deep learning application, for which we basically deploy a cluster of virtual machines. And the required software packages, such as Horovod, will be deployed on these machines within Docker containers. And using Docker containers basically means that this is a highly portable solution. Among the nodes of the cluster, we will appoint one Horovod master, which will have a few extra functionalities. One of these is that a Jupyter Lab development environment will be launched on this node. This will basically act as an interface for the user. This is where they can control the cluster from. Additionally, it will only be the Horovod master where our training data and code is physically stored. And then we will utilize the network file system in order to share these files over the network. I mentioned that Horovod utilizes data parallel training, which means that all the nodes in the cluster has to have access to our training data. This architecture also enables the utilization of GPU resources, but thanks to the previously mentioned customization, the user has the option to turn this on and off before deployment. So if they only have access to CPU resources, they can still utilize this solution. There's also a monitoring solution included. Of course, this is very important for resource-intensive operations such as deep learning. The monitoring system is based on Prometheus and Grafana, and it shows you a variety of different metrics, such as the utilization of the GPU card or the network traffic that happens throughout the training. And it was important for us that users are able to track the resources of their compute nodes during the training. To turn you a little bit towards our research, we have conducted a pretty thorough performance evaluation of this Horovod reference architecture, for which I would like to first present the environment. The experiments were executed on the ELKH cloud, and we used 1 to 8 virtual machines. Each of the virtual machines had an NVIDIA Tesla V100 GPU card, and the nodes were connected by a 10 gigabit per secondum network connection. For actually measuring the performance, we used official TensorFlow benchmark scripts, and we trained ResNet or residual network models, which are very commonly used in computer vision, the computer vision field of AI. As for the parameters that we have examined, one of them was the actual number of nodes in the given training, since in distributed training, one of the most important factors, as we have mentioned before, is the scaling efficiency. So we wanted to see how efficiently the training scales from 1 to 8 nodes. Another one is the batch size. The batch size basically determines the number of samples that get processed before the model is updated. And we used two different values for this. 32 was the default value, but we also pushed it up to the physical limits. The maximum value is 196. So the limiting factor here was the memory of our GPU cards. This was the most amount of data that fit them at one time. And basically, if you remember back to how Horovod works, each of the worker nodes computes individually the model gradients, and then they will update the gradients in a synchronization step. Basically, the batch size in a distributed training determines how much individual work is done before we do the synchronization step among the workers, and this will have a significant meaning in the next few slides when I go over the results. As for the data sets, we used data sets from classic image classification problems, the CIFAR10 dataset and the ImageNet dataset. The example you see on the right side is that of the CIFAR10 dataset where you have 10 different classes, basically different objects, and a lot of pictures in each of the classes. Our goal here is basically to train a model to be able to classify a new picture into one of the classes that it has learned before. The ImageNet dataset is very similar in structure, however, it is significantly larger in size, as you can even see on the physical size, while CIFAR10 is only 170 megabytes, ImageNet is more than 140 gigabytes. So there's a significant difference there. As for the parameters we have measured, of course, there was the raw processing performance. Basically, this means how many images we process per second. There's the scaling efficiency, how well the training is being distributed, and then, of course, the model accuracy, since no matter how good the processing performance gets, it is not worth it if it degrades the model accuracy, because basically the accuracy of the model is what determines how well is it as an output. As for the actual results, starting with the raw processing performance, here we performed the experiment scaling from 1 to 8 nodes, and we checked the results with 2 different batch sizes. As you can see, using the 32 batch size that can be seen on the left side, our scaling was very inefficient, as when using 8 nodes, we only achieved 20% of the ideal value, which would mean 8 times the performance of a single node. This basically means that 4 out of 5 GPU cards is completely wasted, which is, of course, a huge problem. But we found that by increasing the batch size to the physical maximum, 196, we have achieved much, much greater results. You can see that up to 4 nodes, we have achieved more than 90% scaling efficiency, but even at 8 nodes, we have achieved 73%. So the reason for this is basically what I explained before about the batch size. Basically, the larger the batch size, the more individual work is done before there's a communication step. As it turns out, in our case, the weak point of the system was the network connecting these nodes, meaning that the communication steps were taking a significant amount of time and they slowed down the whole process. So by increasing the batch size, we made the communication less frequent, the workers perform more work individually, and so we have achieved a much greater scaling efficiency. So basically here, achieving great performance was a question of optimizing the training parameters. As for the model performance, of course, accuracy was also examined, and we were interested in whether increasing this batch size would have a negative effect on the accuracy of the resulting model. In this case, we always performed the experiment of 8 nodes and evaluated the accuracy of the model after each epoch. One epoch basically means processing the entire dataset once. As it turns out, as it can be seen on the left side, turning the batch size to a significantly higher number does have some noticeable negative effects in the first 4 epochs. However, after that, the results are close to identical, and they have reached the 75% training accuracy both after 8 epochs. The 75% accuracy was our target for this training. However, the graph on the right side tells a whole another story, since thanks to achieving much greater processing performance with the larger batch size, the training time that it took to reach the target accuracy was significantly reduced. With the 196 batch size, we have achieved the target accuracy with a little more than 16 hours, while with the 32 batch size case, this took more than 68 hours. So there's a significant difference there. So we have gained significant time advantage with not noticeable differences in accuracy. Based on our experiences and the positive feedback, the Horovod solution was also published on the EOSC marketplace under the name Distributed Deep Learning by Horovod as a service. We provide a few different modes of access for this service. There is option for a limited time demo, basically a 1 or 2 week period on which our cluster would be hosted on the ELKH cloud. This would be a 4-node cluster, each with 1 GPU, and users could try out the system or familiarize themselves with Horovod. There's also an option for long-term deployment in which the user would provide us access to a cloud resource they own or a project they have access to, and we would install them Horovod into this cloud, and they can utilize it on the long term. There's also an option for self-hosted, during which the user simply follows the published user manuals and deploys the system for themselves in their own cloud environment of choice. But of course, for all of these options, we provide a technical consultation. With that, I would like to turn our attention to a small demo or demonstration to show you how this system actually works. For this, I will quickly grab my browser window. So for the purposes of this demo, I have deployed a small cluster onto the ELKH cloud. You can see that we have a cluster here consisting of 4 nodes, 1 master, and 3 workers. I also have a separate server up here, which is dedicated to the monitoring. Now, if we use monitoring, we preferably want to use 2 public IP addresses, as they can be seen here, and the user will be able to access both the JupyterLab interface and the monitoring solution with the web browser simply. So for example, if we go to the public IP address of the Horovod master, we'll be welcomed with the JupyterLab interface that is hosted on the Horovod master. Of course, first the user has to log in. This can be done with the password that they have configured previously. Since we knew that Horovod would be published as a service for the general public, we made a couple of extra features and took a couple of steps in order to make it more easy for a new user to start utilizing this cluster. And one of these steps was creating this welcome page, which is basically a notebook. When the user first logs in, this is the screen that welcomes them. This is basically a pretty lengthy user manual that presents them the service, tells them exactly what kind of software is installed here, and what are the features of the cluster. It also includes a pretty lengthy guide on how to actually utilize the cluster, for example, how to prepare the training data and code, and where they can find the different features of the cluster. And of course, there's also a tutorial about actually performing some distributed training along with the few different flags that are needed for executing the commands and such. Now there's a few other things that make it easier to use the cluster. For example, we have prepared an automatically generated text file. I'm gonna make this a little larger. Basically what this is a human readable summary of the nodes of the cluster and their most important resources. It is basically a list of the virtual machines that was deployed for the user, and then the most important resources, for example, how many GPU cards are in the certain machines, what kind of GPU cards are there, how much memory they have, how much storage is available, and so on. So each node in the cluster is listed here along with the most important resources. We typically use homogeneous nodes, so the resources that can be seen in the individual nodes are the very same. The Horovod master is one exception because it has a larger storage volume in order to actually store the training data. But the actual size of the storage attached to these machines is customizable again through the parameters. Another helpful thing is a so-called host list file, which is basically a list of IP addresses. These are the IP addresses of the 4 nodes of this demo cluster. This is also automatically generated when deploying the cluster. Why this is needed is because Horovod needs to know the IP addresses of all the nodes of the cluster when you are performing distributed training. Traditionally, you would have to supply all these addresses by hand by listing them in the command. Of course, at 4 nodes, this is already problematic, but typically people even use more. So 8 nodes, it would be close to impossible to memorize all these addresses, and it would be pretty tedious to list them by hand for Horovod. So we provide an automatically generated file, and the users can simply supply this file, and Horovod will read out the IP addressing information here. You can also see an additional flag, which is slots equals 1, which is basically determines how many processes should be started on the given node. So for example, if we have a virtual machine with 1 GPU, that would mean that we want to start 1 process on the given node. This is also automatically filled out. Now, other than these few extra helpful things, the environment is basically your usual Jupyter Lab development environment. You can work in notebooks and start up a terminal. For this occasion, I have prepared a small training script, which is a very simple TensorFlow example training. This is one of the simple examples that are provided by default together with the repository, and they nicely demonstrate exactly what kind of changes you have to apply to your code in order to execute it with Horovod in a distributed fashion. So you can see that it is even commented where there was some modification regarding Horovod. There are multiple of these simple examples included in the repository. So, for example, a user can check these out and learn how to transform their code in order to work with Horovod. Now, typically, the process would begin by preparing some training data and preparing some training code. I'm gonna skip these steps right now, and we're gonna jump into the exciting part, actually performing some executed training, for which I will start a new terminal window. This basically opens up a terminal window for us in the very same folder that you can see here in the file browser. And then we can already, since we have our training script I just presented, we can start Horovod. This can be done using the Horovod run command. Of course, this has a huge number of different flags and options that you can customize. For now, I will stick to the basics and show you how it works. So we have to supply a number of different flags for this command. The first one is this NP flag, which basically stands for the number of processes. So this stands for the total number of processes to be started, meaning that if I have, in this case, for example, 4 virtual machines with 1 GPU each, that would mean 4 processes in total. So that's what I'm gonna write here. Next, we have to supply some information about the nodes of the cluster. Now, traditionally, I would have to do this with the H flag and then simply start listing the IP addresses of the nodes right after each other. But as I mentioned, we provide a nice utility to not have to list all the IP addresses to make it easier. So we can use the host file flag and then supply the previously seen host list file from which Horovod will read out the required information. Next, we have to specify with the pflag port, and this port will be used by the Horovod nodes to communicate among each other on the network during the training. on our system, this is always set up to 1, 2, 3, 4, 5. Basically, here setup means that during the deployment of the system, there is a network rule or firework rule created, which opens up this port between the machines so they can communicate freely. Lastly, we have to specify the executor, which is Python in this case, and the actual training script itself, which will, in this case, will be this TensorFlow2 mnist.py. Basically, with the basic example, I am done. So I can execute this command. And following a few informative messages, which are basically telling me that TensorFlow is loading up, our training should start up. Yeah, right now our training is ongoing. You can see the steps being printed out. And in the meantime, if I go over to our monitoring solution, here the user again has to log in with their configured password. And here we can see the Horovod dashboard that is included in the system. And we can already see that our GPU utilization is above 82%. So we can see that the training is ongoing. We can also see in the top right corner that there is some network traffic ongoing. So the user can basically monitor here their resources during the training. Of course, this was a very simple, short example, but in a real-life application, these trainings could go on for days or multiple hours at least. So it's important to keep track of our machines. And with that, our training script is now complete. And I think that concludes my demonstration. This is basically the basic functionality of how our Horovod system works. So I'm going to jump back into the presentation. And with that, I would like to thank you very much for your attention, and I'm very happy to answer your questions if you have some.